Welcome everyone to a new technical tutorial on this channel. In today's video, we are going to use the same DC motor, controlled in speed using PWM via the Schneider PLC, with the power stage driven by the IRFB 4710 MOSFET. However, this time it will be used for another purpose. The new component in this video is the photoelectric sensor, used as an optical rotary encoder. Optical rotary encoder operating principle. An optical rotary encoder is a non-contact sensor used to measure the rotational position, speed, or number of revolutions of a rotating shaft. It consists of three main components. Photo LED, emitter, produces a continuous beam of infrared or visible light. Graduated slotted disc, a rotating disc mounted on the shaft. The disc contains evenly spaced slots or transparent sections separated by opaque material. Phototransistor, receiver, detects the light transmitted through the slots in the rotating disc. Operating principle. The photo LED continuously emits a light beam toward the phototransistor. The graduated disc rotates between the emitter and the receiver. As the disc rotates, when a slot aligns with the LED and the phototransistor, the light passes through the slot. The phototransistor receives the light and turns on, causing the output signal to change state, typically high or low, depending on the circuit configuration. As the opaque section of the disc moves into the light path, the light is blocked. The phototransistor turns off, and the output changes to the opposite logic state. This sequence repeats for every slot as the disc rotates, producing a continuous series of digital pulses. Each transition between light and dark generates one pulse or one edge that can be counted by a microcontroller, PLC, or electronic counter. Hashtag pulse counting. If the encoder disc contains n equally spaced slots, one complete revolution produces n pulses. For example, 20 slots produce 20 pulses per revolution, 60 slots produce 60 pulses per revolution, 100 slots produce 100 pulses per revolution. The rotational speed can be calculated using the following equation. Speed RPM equals pulse frequency 60 slot number of slots, where pulse frequency is the measured number of pulses per second, hertz. Number of slots is the total number of graduations on the encoder disc. Advantages: non-contact operation with no mechanical wear, high counting accuracy, reliable operation at high speeds, immune to the mechanical bouncing found in contact switches, long service life, simple interface with PLCs, microcontrollers, and other digital electronics. Applications. Optical rotary encoders are widely used in electric motor speed measurement, shaft position sensing, CNC machines, robotics, industrial automation, conveyor systems, printers and scanners, motion control systems. The output of the sensor is a clean digital pulse train. By counting the number of pulses, the controller determines the angular position or the number of shaft revolutions. By measuring the pulse frequency, the controller calculates the rotational speed of the shaft. I think you now have a clear idea of what today's video is about. We're going to use an optical rotary encoder to measure the speed of a DC motor using the Schneider PLC TM221CE16T. Specifically, we will use its high-speed input, I/0, configured in the program as a high-speed counter HSC, operating in frequency measurement mode. By measuring the pulse frequency generated by the optical encoder, the PLC will calculate the rotational speed of the DC motor. Open EcoStruxure Machine Expert and create the hardware configuration by selecting the TM221CE16T PLC. In this project, the PWM control for the DC motor is already programmed. This allows us to change the motor speed by adjusting the duty cycle, so we can measure the different speed values. Before adding the counter object to the project, we are going to configure it. Go to the Configuration tab. On the left-hand side, select High-Speed Counters. In the middle window, click on the three dots and choose the HSC type as frequency meter. For the time window, select 100 milliseconds. We can see that the assigned input is I/0. Go back to the programming mode and add the high-speed counter block from the top library into the program. Connect the IN input directly so the block will remain active all the time. Add a normally open contact to the S input, which is the reset input. Assign any address you want to this contact so it can be accessed from the network. For this application, we do not need a lot of configuration for the HSC block. Add an expression block to calculate the frequency per revolution and store the result in address sent MW21. We divide the measured frequency by 448 because the encoder disk contains 448 slots. As you can notice, the frequency calculated by the HSC is stored in the variable HSC0.V. Add another expression block to calculate the motor speed in RPM. Here, we multiply the value stored in sent MW21 by 60 to obtain the speed in revolutions per minute. Download the project to the PLC and let's start the test. Do not worry, we will come back later to explain how to connect the sensor hardware. On your smartphone, start the Modbus TCP IP mobile application and connect to the PLC. Activate the frequency generator, set the first speed value, and check the result of the frequency meter and the calculated motor speed in RPM. The app is available for free on the Google Play Store. You will find the link in the description. With the app, you can also read the speed in RPM. On your smartphone, go to the Read Register tab, set the address to read to 22, and click the Read Register button. Here, we can see that the motor is rotating at a speed of 2640 RPM, with a duty cycle value of 50%. The sensor is supplied with 5 volts, and according to the rotation speed of the disk, it generates square wave pulses, switching between 0 volts low and 5 volts high. This circuit is a signal adapter that converts a 5-volt TTL sensor signal from an encoder or optical sensor into a 24-volt NPN syncing signal, suitable for a PLC or automation controller high-speed input. The main component of this circuit is the P2N222A NPN transistor, which is used as an open collector switch. 1. Input signal from the sensor. 0.5 volt, the sensor provides a square wave signal. 5 volt equals sensor on, 0 volts will sensor off. This signal is connected to the transistor base B through a resistor. RB equal 1 kiloohms. The base resistor limits the current flowing into the transistor, protecting the sensor output. When the sensor output is 5 volts, high. Transistor operation, a current flows into the transistor base. The P2N2222A turns on and enters saturation mode. The collector C is internally connected to the emitter E. Because the emitter is connected to 0 volts, GND, the collector voltage is pulled down close to 0 watts. When the sensor output is 0 volts low, transistor operation, no base current flows. The P2N222A turns off. The collector is disconnected from ground. The collector voltage is now determined by the pull-up resistor. Our pull-up equals 4.7 kiloohms. This resistor is connected between 24 volts and the collector. The pull-up resistor raises the output voltage to 24 volts. The PLC input must be a 24 volts NPN syncing input. The PLC input provides current internally, and the transistor pulls the input down to 0 volts when it is on. If the PLC input is PNP sourcing, this circuit will not work. In that case, a different interface, such as a PNP transistor stage or an optocoupler, is required. Now, we will perform a test using a smartphone. We will set different duty cycle values and read the speed feedback measured by the optical sensor and the PLC. This will allow us to verify that the motor speed changes according to the PWM duty cycle and that the measured RPM is updated correctly. This is the wiring diagram for the signal adapter. It converts the 5-volt pulse signal from the optical sensor into a 24 volts pulse signal that is compatible with the PLC's high-speed input. This is the PWM power stage for the DC motor, built using an IRFB 4710 MOSFET transistor. That's all for today's video. I hope the steps were clear and well explained. In the next video, we will probably learn how to control the speed of a DC motor while lifting a load. We will use the same Schneider PLC and the same PWM power stage, but this time we will implement PID speed control. If you found this video helpful, don't forget to like, subscribe, and leave a comment. It really helps the channel. Thank you for watching, and I'll see you in the next video.